All right, so I'm going to go through some of these problems that were on the kinematics quiz practice. For reference, I am taking these problems directly from the book so that you can reference it to see the exact numbers that I'm using. Of course, your Mastering Physics might have different problems or different numbers, so just make sure you pay attention to that. Okay, so for my number 31 in chapter 2, I have a graph, and so it starts out at 4 and drops down to 4 on the t-axis. Okay, so now how do I get the velocity if the initial velocity was 8 meters per second? Okay, and so the trick is, well, if we go back to our hierarchy of position, velocity, acceleration, again, going down the hierarchy is derivatives. And then going up the hierarchy is antiderivatives. Okay, we remember that. Now, on a graph, what do these operations mean? Remember that a derivative on a graph means the slope. So that means if we're trying to get the velocity from position, right, so going from position to velocity, it's the slope on a position graph. Likewise, if we're trying to get the acceleration, it would be the slope on the velocity graph. Going backwards, remember antiderivatives on a graph would mean the area. So if I'm trying to get the velocity from the area graph or from the acceleration graph, it would be area. And if I try to get position change from velocity, it would be area. Now the important thing to remember is that the area does not tell you a specific position or a specific velocity. It tells you the change in those things. So if I have this acceleration graph and I find the area, it's going to tell me the change in velocity. Okay, not a specific velocity. So let's go ahead and calculate the area. So it's simply a triangle, so half base times height. Base is 4, the height is 4. So our area is 8 meters per second. That means that our velocity changed by 8 meters per second. So our final velocity then is going to be whatever we started with, our initial velocity, plus this additional change. So that's 8 meters per second plus 8 meters per second for a total change of, or for a final velocity rather, of 16 meters per second. All right, the next problem, number 33. We're given a position function. All right, for part A, it's asking us to find the position at 2 seconds. So we're simply going to plug in 2 for all of our t's. Crunch out the numbers, and we get 21 meters. All right, for part B, we're trying to find the velocity at 2 seconds. Now, before we do that, we need a velocity function. So remember that to find that, we need to take a derivative of the position function. And notice, this is very important, I'm not plugging in the value for t yet. I need to get the function before I can plug in the value. So if I take a derivative, I'll get 6t squared plus 2. Now we can find the velocity at 2 seconds. Crunch it out, 26 meters per second. And finally, part C wants us to find the acceleration at 2 seconds. So same thing here, we need the function first. So I'll take the derivative of velocity. It's 12t. Now I can calculate it at 2 seconds, and I'll get 24 meters per second squared. All right, let's go on to number 34. So here we're given a velocity function and told the initial position is 1 meter. All right, so for part A, it wants us to find the position at 1 second. So before we do that, we have to find the position function. And remember, that means we have to take an antiderivative of the velocity function. So if I do that, that's 2t cubed over 3 plus a constant. Okay, and of course we find the constant by looking at that initial condition. So the initial position is 1, so that means x at 0, the position at 0 is going to equal 1. So let me plug in 0 for all the t's and solve for c. and it's easy enough. C is 1 meter. All right, so my position as a function of time will be 2/3 t cubed plus 1. Now I can evaluate what the position is at 1 second. And you should get around 1.7 meters. All right, part B wants to know the velocity at 1 second. So we go back to our original given function for velocity and plug in 1 for t, and we simply get 2 meters per second. Finally, what's the acceleration at 1 second? All right, we need an acceleration function, so take a derivative of the velocity. You'll get 4t. And now we can find the acceleration at 1 second, and we'll get a value of 4 meters per second squared. All right, let's go to 41. So 41 gives us an acceleration function. Okay, and we're told that it starts at position 0 and it's initially at rest. So for part A, we want to find the next time that the particle is at rest. So in order to do that, we need to find the velocity function first. So we're going to do an antiderivative and add our constant. But we can quickly, because everything has a t attached to it, if we put in 0 for t, velocity has to be 0, that means our constant is 0. So our velocity is a function of time, 10t minus 1/2 t squared. All right. So we want to find out, when is this function equal to 0? So if I factor out the t, you get 10 minus 1/2 times t. So what two values of t will give me a value of 0? The first one should be obvious. It's when t equals 0. And the next one would be, if I solve that term in parentheses equal to 0, you'll get t equals 20. Okay. Now, out of these two times, which one do I pick? Well, remember, it asks for the next time the particle is at rest. We already knew the particle was at rest at t equals 0. That was given. So the next time is at 20 seconds. Okay, and then for part B, it wants to know what is the position at that time. So we need a position function. So we're going to do another antiderivative of the velocity. So 10t squared over 2 plus 16t cubed, and then add a new constant. But just like before, we know the constant is going to be 0. Everything has a t attached to it, so c will equal the initial condition, which is 0. So my position function is 5t squared plus 16t cubed. All right, so then we plug in 20 seconds for t. And you should get a value of 3,333 meters. Okay. Number 49. Okay, so in this case, we have a car driving on a road. It sees a deer 35 meters in front of it. The car was initially moving at 20 meters per second. Okay, and it wants to know whether or not it hits the deer, and if it doesn't, by how much room does it have. Okay, so for the reaction time window, they take 0.5 seconds to react. The deer's out here. Okay, so in order to solve this problem, we simply just have to look at where is the car going to be when it stops. Okay, and in the second window, it can decelerate at 10 meters per second squared. Okay, so we simply need to solve for x2. And as long as x2 is less than 35, then you did not hit the deer. So let's start with the first window before you react. Okay, now I'm going to write out the whole equation, but hopefully you kind of see the pattern. If there's no acceleration, that whole first term is going to go away, and we started at 0, so the last term goes away. So the position is simply the velocity times the time. So that's 20 meters a second for half a second. for a distance of 10 meters. Okay, now after the reaction, okay, let's list out our variables. So we're starting at the position of 10 meters. We don't know where we end. We know we start with a velocity of 20 meters per second. We're going to end with no speed. The acceleration is a negative 10 meters per second squared. And we don't know a time. So if we're going to look for x and we don't have t, we can use the kinematic equation without t in it, which is v squared is equal to the initial v squared plus 2a times the displacement. Okay, and we'll do some algebra here to solve for the change in x. And then we plug in our numbers. So our displacement is going to be 0 minus 20 squared over 2 times negative 10. So it's a negative 400 over a negative 20, which means we get a displacement of 20 meters. So if we displace 20 meters from where we started, that means the car ends at the position of 30. So to answer the question, by how much did we miss the deer? So that's what part A wants to know. So hopefully this is pretty easy. The deer's at 35 meters, the car's at 30 meters. So the distance between the car and the deer when the car stops is a grand total of 5 meters. Sorry. Okay, so now the part B wants to know how fast can the car be going, the maximum speed of the car, such that it can still stop before hitting the deer. So same basic problem, only this time we don't know what v is. Oops. Sorry, jumped ahead there. Okay, so how do we figure this out? We know the reaction time is still half a second. Your speed is still going to be an unknown, but we can still decelerate at 10 meters per second squared, and we're going to stop at the end. Okay, so first we need to figure out what our new position is going to be. So again, you don't have to do all these steps because if there's no acceleration, it should be easy. X is v times t. Now we don't have a value for v, but it doesn't mean we can't hold this place. In other words, the final position before we react is just going to be the velocity times half a second. Now that's as far as we can take it. We don't have a value, but that doesn't mean we can't use that. Okay, so now let's jump to the second part, when we are putting our foot on the brake. So we've got two positions, two velocities, and acceleration time. So we're starting at the position of 0.5 v. Again, until we know what v is, that's the best we can do. We know we have to end at 35 meters or less. Our initial velocity is whatever we're starting with, which is just v. We're going to stop at the end, so v2 is 0, and the acceleration is negative 10 meters per second squared, and we don't know anything about time. So again, if we don't know anything about time, we can use the equation without t in it. Okay, now what we're going to do here is rather than solving for the delta x, we want to solve it for v. So final v is 0. The initial v is just our unknown velocity, which is what we want, plus 2 times the acceleration, which is negative 10. And change in x, I mean, its change is final minus initial. So let's write it that way. x2 minus x1. Okay, so I've got v squared minus 20 times x2, which is 35, minus x1, which is 0.5 v. So we're going to distribute that negative 20. Okay, and so negative 20 times 35 will be negative 700, and negative 20 times negative 0.5 v would be 10 v. So if you notice, this is a quadratic equation in the term v. So all we need to do is use the quadratic formula to solve for v. So you can go ahead and do that, negative b plus or minus square root b squared minus 4ac all over 2a. And when you do that, you should get two answers. You're going to get negative 32 and a positive 22. Now, out of the two of these, only one of them really makes sense. Now, of course, you could be going any speed in the negative direction and never hit the deer. Okay, so we're trying to talk about heading towards the deer. So the negative number is not possible based on what we're trying to look for. So that means the maximum speed you could go is 22 meters per second and still be able to stop before hitting the deer. Okay, let's go to 53. So here we've got two animals. Now, I'm not even going to try to draw these, so I'm just going to say that this box with the C represents the cheetah, and the cheetah is moving at a speed of 30 meters per second. Say we'll start at position 0. And the gazelle is at a position of 170 meters, and it's starting at rest. Okay, so here's the trick. So the gazelle will accelerate for 5 seconds. Okay, and so during that 5 seconds, we need to know, where does the cheetah end up? Okay, so let's list out our quantities. And these are just for the cheetah. And we're going to solve it for the position of the cheetah after the gazelle has been accelerating for 5 seconds. So 30 meters a second for 5 seconds means the cheetah is located now at 150 meters. Okay, so now where is the gazelle going to be after it's done accelerating for those 5 meters? Or, excuse me, accelerating for those 5 seconds. So it starts at the position 170. It starts at rest. It accelerates at 4.6 meters per second squared. I didn't write that in the picture, but that's given in the problem. And it's going to accelerate for 5 seconds. So a couple things. One, how fast is it going after it accelerates? So I plug in the acceleration, which is 4.6 meters per second squared. Meters per second squared for 5 seconds. And when I crunch this out, I'll get 23 meters per second. Oh, I didn't write meters per second there, but I wrote it there. Okay, 23 meters per second. Now, what is the final position of the gazelle after it was accelerating? So you can really use any kinematic equation here, but I'm going to use this one. So I get 1/2 the acceleration times time squared plus the initial velocity plus the initial position. And when you crunch all this out, you find that it's at the position 227.5 meters. Okay, so we found out where the gazelle is and where the cheetah is at the moment the gazelle stops accelerating. Now, the problem tells us the cheetah can go at this constant speed for 15 seconds. 5 of those seconds have just been used. So now we have to ask, where are the cheetah and gazelle going to be during the next 10 seconds? Okay, because if the cheetah catches the gazelle, then the final position of these two animals should be the same. Think about that. If the two animals meet each other, if the cheetah gets to the gazelle, they're at the same position. So if they get to the same position, the cheetah caught the gazelle. So let's find out what those two positions are over these next 10 seconds. Now, both animals moving at a constant speed. So that means no acceleration. Moving at a speed of 30 meters per second for 10 seconds. And it's starting at the position of 150 meters, because that's where the gazelle or the cheetah was after the gazelle accelerated. So that means the final position of the cheetah is 450 meters. Okay, let's do the same thing for the gazelle. The gazelle is no longer accelerating. It achieved a velocity of 23 meters per second. Remember, we solved that after it was done accelerating. And it was at the position 227.5 meters. So crunch all that out, and we find out the gazelle is at 457.5 meters. Now, when I checked my answer in the book, it turns out the book rounded that number up to 460. So I kept it this way, but I guess the book wanted it to two significant digits, so it was 460. But if you figure this out, it says that the gazelle did get away because the gazelle was, by my numbers, 7.5 meters in front of the cheetah when the cheetah gave up. Sorry, I didn't mean to jump forward. Okay, so yeah, the gazelle gets away by a total of 7.5 meters. And again, the book says in the back that it was by 10 meters because it rounded 457 to 460, so that is a 10-meter difference. All right, let's go to 64. Okay, so in 64 we've got a car, a getaway car, driving at 50 meters per second at a constant speed, and they notice a nail strip, right? It's a bank robber getting away at 50 meters per second, and the police have set up a nail strip in front of the car. Okay, and I think it's 150 meters away. Okay, so kind of the same thing with the deer. The question is, does this person stop before they get to the 150 mark? So what we're going to do is we're actually going to solve for the x2 and try to figure out what is their final position and how that compares to the 150 where the nail strip is. All right, so while the car is moving at a constant speed, in other words, before he reacts, we're going to figure out where he's located. Okay, so the velocity is 50 meters per second. It takes him 0.6 seconds to react. So he's going to be located 30 meters from where he started. All right, now, while he's decelerating, again, we want to know if he starts at the position 30 meters, where does he end? So he starts with a speed of 50 meters per second. He's going to slow down to 0, and he has an acceleration of negative 10 meters per second squared, and we don't know anything for time. So we'll use the equation without t and solve it for the change in x. Okay? So if we plug in our numbers, the final speed is 0. The initial speed was 50. Divided by 2 times the acceleration. And we get a displacement of 125 meters. So the final position then is going to be the position we started at, which is 30 meters, plus this additional displacement. So we started at 30. We ended at 125. Or 125 later, so that means the final position of the car was 155 meters. Well, if the nail strip was initially 150 meters in front of him, it turns out that the driver stopped 5 minutes after the nail strip. So he was caught by the cops. All right. So, final problem, number 68. All right, so in this case, we've got two drivers, David and Tina. David is driving along at a constant speed of 30 meters per second when he passes Tina, who's initially at rest. Okay, now, David has no acceleration going at constant speed, but Tina can accelerate at 2 meters per second squared. So what we want to do is figure out how far Tina has to drive until she catches up to David. Now the idea there is that when they reach this final position, they will be at the exact same final position because that's when Tina has caught up to him. We don't know how fast Tina is going to be going at that point, but we do know that David is going the same speed because he's going at constant speed. Okay, so when we write out our equations, we're going to list out the information for David. Okay, so David starts at the origin. We don't know his final position, but we do know he's going at a constant speed of 30 meters per second. So A is 0. Now let's do Tina's information. Tina starts at the same position. Now we don't know where she ends. We know she starts at rest. We don't know the speed she's going to have at the end. We know she can accelerate at 2 meters per second squared, but we don't know the time it takes for her to catch up to him. Now the key here is to recognize that when Tina catches up to David, the final positions are going to be the same for both drivers. So the way to solve the problem would be, well, if they're catching up to each other, the two x1s are going to be equal. Well, if these two numbers are equal, it follows that the equations to get those numbers must also be equal. So on the left side, we've got the equation for David, and on the right side, we have the equation for Tina. All right, so let's go through on David's side. David's not accelerating, so that whole term is going to be 0, and he starts at the origin. For Tina, she starts at rest, and she also starts at the origin. So this reduces the whole equation down to David's speed of 30 meters per second times the time equal to half of Tina's acceleration times the time squared. So what we need to do here is solve for t, because that'll tell us the time it takes for them to get to the exact same positions. So if I move the 30t to the right side, I'll get half times 2, which is just 1, times t squared, minus 30 times t. Now the trick to this would be solve this equation. Well, I could factor out a t, and I'll get 1 times t minus 30. So the two times when they're at the same position will be when t is 0. Well, that's obvious, because if you look back at the picture, when t was 0, they both were at the same position. So we already knew that answer. But now if I solve the term in parentheses for when it's equal to 0, we'll get t is 30 seconds. So again, t is 0 when David passes Tina at the start of the problem. They're at the same position at that point. And then when t equals 30, that's the point when Tina has finally caught up to and is passing David. So, to answer the question, how far does Tina have to drive? Okay, what we're going to do is go back to Tina's data, add in the time of 30 seconds, and simply solve for her position. So I'm using the exact same equation I just used, only now I can actually solve for what the final position actually is. So same thing, she starts at rest, she starts at the origin, so it's simply 1/2 times the acceleration times the time, which is 30 seconds, squared. And we get that her final position is 900 meters. So she traveled 900 meters before catching up to David. Part B wants to know how fast she's going to be going when she reaches David. So we're simply going to set up same set of information, same table, only now we're going to solve for the velocity. So acceleration is the same, it's 2 meters per second squared, and she still starts at rest. And we know the time is going to be 30 seconds, so she's going to be accelerating for 30 seconds, which means her final speed is going to be 60 meters per second.